Hello students, welcome to my channel. This is mathematics education provided to you by Umar Adam Umar and prepared for Ethiopian grade 12 students who are gonna take the Ethiopian University entrance examination. The lesson presented here is directly related to the entrance examination, both from the previous one and the expected one this year. I hope you will follow attentively and watch the video to the end. Here, before we go even further, let us begin the lesson from grade 12 mathematics unit 1 by discussing the main concept included in the chapter. Now the chapter deals with sequence in the series. There are two words connected by and here. Therefore, we will see both words separately. First, let us begin with the definition of the sequence. The word sequence in everyday conversation usually refers to a list of things occurring in a specific order. But in mathematics, the sequence is a set of numbers. One comes after another in a given rule. We also define a sequence as, let us say, as a function whose domain is the set of positive integers. As you can see here, the definition. The sequence is a function whose domain is a set of positive integers. It is usually represented by a subscripted letter in braces as such, an braces in braces a sub n, where an represents the n terms or the nth terms, and we call sometimes the general terms, and the functional values or the range of this function, the sequence function, are a1, a2, a3, an, and so on. And these are called terms of the sequence, where a1 represents the first term, a2 represents the second term, and so on, and an represents the nth term. Now let us see some of the examples. As you can see here, there are three examples provided particularly for this section. In A, as you can see, the list of this number, the number listed here indicated the sequence, which means 5, 8, 11, 14, and 17, and so on. Such a list is said to be a sequence because they are arranged in a certain rule or in a given rule. For example, 8 is obtained by adding 3 on 5, and 11 was obtained by adding 3 on 8, and 14 is also obtained by adding 3 on 11, and so on. This sequence is said to be an arithmetic sequence. We call it an arithmetic sequence, and it can simply be expressed as 3n plus 2, which is called the general term, in terms of the general term in braces. And similarly in B, here 3, 6, 12, 24, 48, and so on. This is also represents the sequence. It represents the sequence. These are terms of the sequences, and it has a certain or a given rule. For example, 6 was obtained by multiplying 3 by 2, and 12 was obtained by multiplying 6 by 2, and 24 was also obtained by multiplying 12 by 2, and so on. This kind of sequence is said to be a geometric sequence. We will see the definition of arithmetic, both arithmetic sequence and the geometric sequence later on. Again in C, as you can see, minus 1, 1, minus 1, 1, minus 1, and 1. These are also, again, these terms are also represents sequence. And we can write the general term as such, minus 1 the power of n. Sometimes we call such kind of a sequence as a vibrating sequence. We call it vibrating sequence. And now let us see the definition of arithmetic sequence, because in the chapter, in the first chapter of grade 12 mathematics textbook, there are many sequences, but among them we will concern it with arithmetic sequence and geometric sequence. Mainly we will focus on these two sequences, although we will also discuss about the recursive sequence here. What do you mean by arithmetic sequence or arithmetic progression? An arithmetic sequence is one in which the difference between consecutive or successive terms is constant, non-zero constants. Actually, it must be non-zero constant, and this constant is called the common difference and denoted by D. Here, this sequence, which is simply given by the general term an, is an arithmetic sequence if and only if the difference between a sub n and a n minus 1 gives us a non-zero constant, which is denoted by D for all n an element of natural number. And the nth term of an arithmetic progression or arithmetic sequence is given by an is equal to a1 plus n minus 1 times D, where a1 is called the first term and D is called the common difference. Also, the sum of the first n terms of an arithmetic progression or arithmetic sequence is simply given by Sn is equal to n over 2 and 2 times a1 plus n minus 1 times D, where n is the number of terms of that sequence. And this can also be, the formula can also be converted in this one. We can either use this one and also this one. Sn is equal to n over 2 a1 plus an. Only now this formula is expressed in terms of the sum. The arithmetic sum here is expressed in terms of the first term and the last term or the nth term, the final term. And moreover, again, the geometric sequence, we will see the definition of geometric sequence or geometric progression. We call it geometric progression. A geometric sequence is one in which the ratio of consecutive terms or successive terms is non-zero constant, and this constant is called the common ratio and denoted by R. That is, for this sequence Gn in braces to be a geometric sequence, now Gn over Gn minus 1 must be equal to R for all n an element of n or natural number. That means this Gn and Gn minus 1 are successive terms of the sequence. Moreover, the nth term of geometric progression is given by Gn is equal to G1 times the common ratio, which is R, the power of n minus 1. And the sum of the first n terms of geometric progression is also given by, here Sn is equal to, in braces, n times G1. This is true if and only if R is equal to 1. If the common ratio is 1, then the terms of the sequence is identical. The terms are identical. They are the same number, and therefore we simply, to find the partial sum, the first n terms of the geometric progression, we simply multiply by the number of terms, one of the terms. And also, if R is different from 1, then the sum of the first n terms of geometric progression is given by G1 into 1 minus R to the power of n over R, or 1 minus R, where G1 is the first term. This can also be written as G1 is equal to R to the power of n minus 1 over R to the power R minus 1 simply. The following are very important points regarding arithmetic and the geometric sequence. Here, to know whether the given sequence is arithmetic or geometric, let us see these very important remarks. If the nth term of any sequence is linear expression, in n, then the sequence is an arithmetic progression. If the sum of n terms of any sequence is a quadratic expression in n, then the sequence is an arithmetic progression. But what do you mean by linear expression in n? Suppose we have two variables. Let us call this one a, let us call this one b, a, let us say this is a and b. Suppose these are a and b, and these are elements of real numbers. Suppose these are elements of real numbers, or simply integers. Let us call them integers. It is better to say like that. Let us call these be integers. Suppose these are integers. These are integers. Suppose these are integers or real numbers, whatever. Now, if we write a n plus here b, then such kind of expression are said to be linear expression in n. Linear expression in n, where our n is natural numbers. Where our n is natural numbers. In any case, a and b can be real numbers, but a must be different from 0. A must be different from 0. In that case, this is a linear expression. Then if the general term or the nth term of any sequence is given as a linear expression in n, then that sequence is said to be an arithmetic sequence. Okay, now let us see again another remark here. Let us see another remark. If the nth term of any sequence is in the form a to the power of n, provided that n is an element of natural number, then we say the sequence is a geometric sequence or geometric progression. That is the difference between the two. One is represented as exponent, and the other represented as a linear expression. A linear expression. Okay. Now let us see again recursive sequence. Another sequence is said to be recursive sequence. As you can see here, a sequence that relates to a general term an of a sequence where one or more of the terms that comes before it is said to be defined recursively. The domain of recursive sequence can be the set of whole numbers. For example, Mulatu and the Fibonacci sequence are some of the examples of recursion formula. As you can see here, Professor Mulatu introduced a sequence of the form mn is equal to 4 if n is equal to 0, and 1 if n is equal to 1, and also mn is equal to mn minus 1 plus mn minus 2 if n is greater than or equal to 2. Now, what are the terms of Mulatu sequence? Let us see here. Let us see terms of Mulatu sequence. The terms of Mulatu sequence can be described as such. Here are the terms. Now let us see. These are some of the terms of Mulatu sequence. Terms of Mulatu sequence can be given as such: 4, 1, 5, 6, 11, 17, and so on. Now, the third term was obtained by adding the previous two terms. Any term will be obtained by adding the previous two terms, the preceding two terms. Now 4 plus 1 gives us 5, and also 1 plus 5 gives us 6, and 5 plus 6 gives us 11, and 6 plus 11 gives us 17, and 11 plus 17 also gives us 28, and so on. That is what we call the Mulatu's term. Okay, the Mulatu sequence, the terms of Mulatu sequence. And let us again see terms of Fibonacci sequence. Now, Another example of recursion formula is the Fibonacci sequence. It is defined as Fn is equal to 1 if n is equal to 0, and also 1 if n is equal to 1, and Fn again equal to n minus 2 plus n minus 1, f of Fn minus 2 if n is greater than or equal to 2. Now, as you can see, these are the terms of Fibonacci sequence. Here, any term can be obtained by adding the preceding two terms. Here, the first term, m0 is 1, m1 is 1, but m2 gives us 2 by adding 1 and 1, and m3 gives us also 3 by adding the two terms preceding 3, and 5 can also be obtained by adding 2 and 3, and 8, the next term, gives us by adding 3 and 5, and so on. These are known as Mulatto's and the Fibonacci term. Now, you students, you may also be asked this year one of these two. In that case, you have to know how to list the terms of each individuals, or keep this one in mind. Keep this one in mind. That is the point. Okay. Now, another thing we must consider here is series. What is series? Series is nothing but it is simply the sum of the sequence is said to be a series. Series can be finite or infinite accordingly. Infinite series can be either convergent or divergent. How? We will see when we say convergence and divergence. Suppose, let us say this be a sequence, n is running from 1 up to infinity, be a sequence. The sum of the first n terms of this sequence is simply denoted by Sn, and this Sn is called the partial sum of the sequence. It is called the partial sum of the sequence. And such summation is denoted by using the sigma notation. As such, Sn is equal to k running from 1 up to n. Ak is equal to a1 plus a2 plus a3 plus a4 plus and so on up to an. This is known as the partial sum, where k is said to be the index of the summation, and 1 is the lower limit, and n is the upper limit. And this notation is nothing but it is simply sigma notation, or in mathematics we call it summation notation. Now, as we have seen earlier, a series, an infinite series, can be converges or diverges accordingly. If when it is divergent, when we call it divergent, when we call it convergent, let us see. Here, let an be an as n running from 1 up to infinity be a sequence. Sn be the n's partial sum, such that as n gets larger and larger, Sn tends to s, where s is real numbers, then we say that infinite series, this series converges, and it is written as here the summation of n is running from 1 up to infinity is equal to s. If the partial sum of this infinite series converges, then the whole series, the infinite series, also converges to the same number. However, if such an s does not exist or is infinite, we say the infinite series diverges. The infinite series, the summation of n is running from 1 up to infinity, diverges. We call it diverges. Okay, the exact all the arithmetic sequence, all arithmetic series diverges because they are linear. The nth term or the general term of any arithmetic sequence is linear expression in n, and therefore as n increases, then the entire expression increases, and therefore that sequence will not be the int number, or it goes to infinity. As n goes to infinity, then the terms goes to infinity without stop, and therefore we call it a divergent sequence. But there are cases in which geometric sequence can either be converges or diverges to a single number, or diverges. Now let us see divergency and convergency of infinite geometric sequence. Considering the infinite geometric sequence, Gn is equal to r to the power of n, where the first term Gn is equal to r, where G1 is equal to r, and the common ratio is r. There are cases of convergency and divergency when n approaches to infinity as follows. If r greater than 1, as n goes to infinity, then the nth term Gn goes to infinity. In that case, the sequence is said to be diverges or divergent sequence. If r is equal to 1, as n goes to infinity, Gn goes to 1 simply because our r is 1. 1 the power of n gives us 1, and therefore it converges because it gives us a single number. And the case where r is in between -1 and 1, that means the absolute value of r is less than 1. That means -1, let me write here, -1, if r is in between -1, suppose this is r, here if our r is in between -1 and 1, can be written mathematically as such. If our r lies between -1 and 1, excluding both endpoints -1 and 1, then as n goes to infinity, Gn goes to 0. In that case, we call it the sequence, the geometric progression or the geometric sequence converges. Here, when in the case where -1, where our r is in between 1 and the -1, the sum of the geometric series, the infinite geometric series, converges to G1, the first term, over 1 minus r. What does this mean? Suppose we have this one. Let us say this. Suppose we have the sum written as such. We have the sum, infinite series. The sum. This is geometric series. If the expression is exponent, in the exponent form, then now suppose this is an. Our n is, let us say our n is running from 1 up to infinity. Sorry for my writing skills here, because I am new to this one. Suppose this is infinity, n is running from 1 up to infinity an. Okay, now this can be converges accordingly. If we replace this an in this form, let us call this one be 1 over here 2 the power of n. Assume that this is 2 the power of n. Now here this is geometric sequence, as it is nth term or the general term is given as 1 over 2 the power of n in exponent form. Then we call it the geometric sequence, and therefore the sum of this infinite series simply gives us nothing. When our n is 1, we will get G1 1 over 2 the power of n, and therefore our G1 is equal to 1 in this case, and 1 over 2, and again our common ratio is 1 over 2 also. So common ratio is also 1 over 2. Our R is also 1 over 2. It is 1 over 2. Let us say this is also 1 over 2. Now how can we find this sum? Is it convergent or divergent? Let us check. As n goes to infinity, 1 over 2 goes to 0, and therefore Gn goes to 0. In that case, this series converges to a certain number. Now what does that mean? S of infinity converges to G1 over 1 minus R. We will deal with this one later on in question part. Therefore, G1 is equal to 1 over 2 and 1 minus 1 over 2. Our R is 1 over 2. And this sequence goes to what? Goes to 1. Goes to 1. It goes to 1. The series, the infinite series, goes to 1. Therefore, in that case, we say it converges to a real number, a single number. Okay. Next time, once these are the whole concept of the chapter. These are the whole concept of this chapter, the important concept of the chapter. It helps us to deal with the examples or questions or problems that are related to the entrance examination, because we are about to do some of the important examples or problems that are related to the entrance examination, and therefore this much concept are helpful to understand how to perform each of the given question, and then we will see this one in part 2 of this the video, and therefore please follow the channel, subscribe to it, like to it, and also share and comment if there are problems. Next time, in our next video, we will see how to solve each of the questions given here, which are directly related to the chapter and also directly to the entrance examination. Some of them were taken from the previous entrance examination for the past 10 years, and some of them are designed and expected to appear on the coming national examination, I hope. And till then, bye bye. See you